Hello and welcome back to AP Pre-Calculus. This is lesson 1.7, Rational Functions and End Behavior. All right, let's do a quick review of Algebra 2 and what a rational function is. So remember, rational, the root word is ratio, and that means it's going to be a fraction. Okay, so a rational function is going to look like a fraction. But it's not just any fraction. It can't have just like a regular number in the denominator, because then we could break that down into separate terms and it would just be a polynomial function. A rational function has a polynomial function in the numerator as well as a polynomial function in the denominator. And the key to the denominator is it has to have an x in it, okay? The numerator doesn't have to have an x, but to be a rational function, the denominator definitely has to have an x. Otherwise, you're dealing with just a regular old polynomial function, which we've dealt with before. So you'll notice that all of these guys down here have x's in the denominator, where a couple of them don't have x's in the numerator, and that's okay. So let's keep going with review. Last year we did end behavior, and remember we are dealing with the leading term, the first term. And when you write a polynomial function, you should be putting the biggest exponent term first, okay, in the numerator and in the denominator. And if you do that, this idea of end behavior is pretty easy. So let's look at case 1 here. It says the leading terms have the same degree. It would be something like this. F of x equals 7x to the 5th and 3x to the 5th. And I don't care about the rest of it because I only care about these first terms, okay? If that happens, then we do have a horizontal asymptote, and we just take the coefficients and we set them equal to y. So we have a horizontal asymptote for this one at y equals 7 over 5. I actually like to think about it as forgetting all the rest of the terms and actually dividing this out. We would cross these x's out, and it even says right here, it says y equals 7/3. So that makes it kind of easy. Case 2 is when the denominator is less than the numerator. The denominator's degree. All right, for example, that would look like this. G of x equals 5x to the 3rd, 10x to the 4th, right? So the numerator is smaller than the denominator. Again, I like to think of this as a division problem. I'm left with g of x equals 1 over 2x. Whenever I have an x in the denominator, we have y equals 0, okay? Horizontal asymptote at y equals 0. Because remember, an asymptote, we cannot touch that, okay? Which means I'll never be able to make this fraction into a 0. I can't do it. 1 divided by anything will never be 0. So that's why we have a horizontal asymptote there. And our last case is if the numerator is bigger than the denominator. I'll make one up. I'll just flip this one around. 10x to the 7th over 5x to the 5th. All right. Again, I'm going to divide, and I'm left with h of x, or y, equals, can't see my 7 anymore, 2x squared. Well, that's a parabola. My arrows, my end behavior, the arrows are both going up. They don't make horizontal anywhere. So in this one, this is a little bit different than what we did last year. Last year, we were able to just say, well, there is no horizontal asymptote, and that is true, but we are talking about end behavior, and our end behavior will it will go to one of the infinities. So then you have to re-examine it after you do the division and go, oh, it's even, and it's positive, so they're going up to infinity as I approach positive infinity on x, so on and so forth, like we've already done. There's one more that we did not do last year, and that is called a slant asymptote, or an oblique. And that is when we have exactly one more in the numerator than we have in the denominator. So look at this one. M of x equals 6x to the 4th, dot, 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 like big old thing. Who cares? over 3x to the third, dot, 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 dot. 4 is exactly one more than 3. This has a called a slant asymptote, and it makes a lot of sense if you do what I've been doing on these other ones, and we just divide. Because I'm going to go m of x, which is really a y, equals 2x. Well, that's a line, right? So in this case, again, our end behavior, one side would go to positive and the other side would go to negative because it's an odd function, so they have to go in opposite directions. So that's the new one right there. All right, so let's put these rules to the test here. So in A, it's written in the right order. All right, if we do the division, we're going to get f of x equals 3 over 5, and that is a horizontal asymptote, right? So remember, if we have an x left over in the numerator, then our end behavior will go towards infinities. If they disappear or it's left over in the denominator, we have horizontal asymptotes, okay? So let's look at the next one. I have y equals 2 over x. Well, that's left in the denominator, so we can say y equals 0 is the horizontal asymptote. All right, so here on C, we have g of x, which you could rewrite as a y. Let's go ahead and put the box over here. I'm left with 2/5 x. Well, that's a line, okay? It's a positive slope line. It goes from left to right, it goes uphill. So if we're talking about end behavior, we'd have to describe the end behavior. But here we're talking about horizontal asymptotes. So here we would say none. It actually has an oblique, if you wanted to be really fancy. Okay, let's look at D. We have y equals, that becomes 1/2. So that's a horizontal asymptote. On C, well, there's nothing really to do. I have an x in the bottom, so I have k to the x equals 3 over x squared. That's y equals 0. That fraction will never be able to be 0. So we have a horizontal asymptote at y equals 0. And last, same deal as the last one. We put a box around this stuff, and I get negative 2 over x. Put an equal sign in there. X is in the denominator. I get y equals 0. That's a 10. Y equals 0. That's a horizontal asymptote. And just as a reminder, our words mean things here. So when I'm asking if it has a horizontal asymptote, if it does, then it's a line. So you have to say y equals. You can't just put 0. You can't just put 3/5. Okay, that doesn't mean anything. You have to put y equals, or f of x equals, or g of x equals, or whatever the notation is. But you can't just say a number. Okay? All right, so now we are going to do the same thing, but we're going to write it a little bit better, right? We are in AP Pre-Calculus, higher level math. I mean, this is some of the highest level math you can take in high school. So we're going to tighten up the way we write things. So if you remember before, when we write, we're going to use a limit statement, and as x approaches to the left, it's going to be negative infinity, and we have f of x here. And the other one will be the limit as x approaches positive infinity. Put our f of x. We want to know, what is it doing? All right. Well, those cancel out, so I end up getting f of x, or y, equals 1/3. So as I go to the left, I level out at 1/3. As I go to the right, I level out at 1/3. That's how you write a horizontal asymptote in a higher level form as you move forward, okay? So I'm going to go ahead and do these next two. You go ahead, pause the video, and give it a shot, and then restart it, and let's see how you did. Okay, here's B. I did my box around those. I ended up with an x in the denominator, which means I'll never be able to turn this into a 0. So y equals 0 is our horizontal asymptote, and there's your limit statement that shows that. And let's look at C for a second. That's a little bit more difficult because this is a slant asymptote, right? So when I do this, I'm going to do it down here. H of x equals, when I do the division, I get negative 3x. don't really care about the rest of this. We might care about it later. We might really care about what the y-intercept might be. So we would have to do long division. But in this case, we're just talking about end behavior. So if I have a graph, and I had you graph y equals negative 3x, it probably looks something like that, okay? So what is my end behavior doing? As I'm going to negative infinity on my x, remember that's this way, as I'm going this way, what is my graph doing? Well, it's increasing without bound. So it is going to positive infinity. As I go to positive infinity on the x, my line is decreasing without bound, so it is going to negative infinity. So that one didn't have a horizontal asymptote, but we were asked to describe the end behavior, not tell if there was an asymptote or not. Okay, a little bit different way to look at this stuff. Let's go ahead and write our limit statements down. Pause the video. All right, I have the beginnings of my limit statements here. So let's look at what's going on. So here I am, it wants to know as I go this way on the x-axis, as I approach negative infinity, what's happening? Am I going to an infinity? Nope, I'm kind of leveling out, and it looks like I'm leveling out at 2. I wonder if we're doing the same thing the other way. As I go to positive infinity, yep, I'm flattening out again right there, and it looks to be at about 2. Come over to E, and like we have some vertical asymptotes here, but that's not part of the end behavior, so we don't really have to talk about those. So as I go to negative infinity, am I going to a positive infinity or negative infinity? Nope, I'm leveling out, flattening, and that looks like it's a -1, and the same on the other side. Pretty easy. Hope you got it. If not, rewatch. All right, our last slide. Back to slant asymptotes, or oblique asymptotes, if you will. We've already talked about them, but this kind of formalizes it and puts it in some really mathy terms. But remember, really the only deal is the degree on the top, the biggest exponent on the top, the numerator, has to be exactly one more than the one on the denominator. Like at some point we're going to have to find the equation of the oblique asymptote, but right now this is just asking, hey, which one of these would be parallel to this line, right? Parallel, remember, this has got a slope of 1/2. To be parallel, the slope needs to be 1/2. So let's go through some of these real quick. All right, is that one more? It is not, so it's not 1. All right, that is not one more, so it's not 2, or yeah, 2. This is one more, and if I do the division, I get h of x equals 1, because there's a 1 in front of that x squared, over 2x, because there's still an x in the numerator. Well, that's 1/2. So this one is good. Let's just check the last one. Oh, I covered it up. That's not one more, so it can't be 4. So the answer is C.